Welcome back. This is lecture 6, I presume, right? Okay. So we were, or is it 5? 6, yeah, fine. Okay. The last one was not marked. So we kind of rounded off the RF chain in the previous lecture. The only part that we didn't touch upon at all is how you generate clocks, right? So essentially what I am talking about is, if I only think about receiver, then you have antenna, you have SAW filter, you have transmission line, some sort of matching network, then an LNA, maybe some another filter somewhere, and ultimately you come to a mixer. And in the mixer, if this is, let's say, if the frequency component here, after all the filtering and all, is at FC plus FBB plus minus FBB, you expect the mixer to be operating at FC, so that after mixing and subsequent low pass filtering, you are able to recover the baseband signal. Again, when I say baseband signal, I essentially mean a signal which is of much lower frequency than FC. And typical examples, FC may be a gigahertz, FBB can be a couple of megahertz, tens of megahertz or so, right? So that's which essentially means that the low pass filter that you are going to have here can be of bandwidth FBB, right? So which is much lesser than FC. So now we had talked about everything, but from how do we generate FC? Okay, so in today's lecture, I'll try to give you a very broad overview of how to go about generating this FC. Later on in the course, we'll go deep into that, right? Just like we are touching base on each of these subblocks in an RF chain, we'll also do something similar for how to generate an FC. So when I say FC, I essentially mean that ideally, I would like to have, so this is generation of a clock having a frequency FC. So when I say you have to generate a clock having a frequency FC, essentially you can think of that I am looking for a block whose output will be VP sine 2 pi FCT. Okay. And VP, there is no such hard constraint on VP, right? Because if you think about this mixing operation that is getting done in the RF chain, if you have VP to be, obviously you don't want VP to be 0, but there is no hard constraint that VP has to be a precise value, right? Higher the better, because ultimately the input of the low pass filter that will come here will also have this VP term multiplied in the multiplication factor. So higher the better, but it's not necessary that VP has to be some precise value. Okay. So what is the so let me ask you, can you think of something that you have already learned from your undergraduate days? What is any block that can generate a sinusoidal signal? An LC oscillator, right? An LC oscillator, perfect, right? So I have an LC oscillator. Let's say I take this L, this is C. So if it's an ideal LC oscillator, you are going to get between these two terminals, you are going to get a sinusoid. What will be the frequency? C will be 1 by 2 pi under root LC, right? Oh, and by the way, what will be the amplitude? How do you know what will be the amplitude? It will depend upon the initial condition, right? If you start off with some charge on the capacitor, right? So that will set the amplitude corresponding to the charge. I mean, charge divided by the capacitance is the voltage to start off, and it will, if it's an ideal no loss LC oscillator, it is going to keep on going for infinity. And if you want to generate an FC, if you want to change an FC, all you have to do is tune L and C, either ALLC or both or combination of them, right? As simple as that, right? If only. So the issue is you do not have an ideal LC oscillator. You always have loss, right? So some R associated with it. And this genesis of that R can be a leaky capacitor, a lossy capacitor, or even the loss through an inductor. You can as well put this some R in series with the inductor. That also will model a loss, right? But just to keep things simple, I'm just putting R in parallel, right? So effect of that will be same for all, but the details will vary. So if I use this R in this way, so what's going to happen to the final output? The amplitude will decrease, right? Great. So essentially, if I say this is V out, your V out with respect to time is going to go down. Something. Will it have any effect on frequency? Why not? Why only amplitude? Why not frequency? But I have added something. How do you know that adding that R doesn't change frequency? Right. So essentially, if you look at the impedance of this, you are going to get a real term and an imaginary term, right? So essentially, that imaginary term will set the frequency. And another way of thinking about it is okay. Let's not get to the other way, but I mean, for now, let's assume that is the reason. I mean, you don't change frequency. So, but which essentially means that if you put R in a slightly different way, which can change that imaginary term, then you can also have a change in frequency, right? So it might be very small or very large, but you have to be slightly careful about it at times. Okay, fine. So let's say there is no frequency change, there is a damping. And this damping will happen, and eventually everything will go to zero. So what is the fix to this? The obvious fix to this is to say that if I can only design a circuit which can cancel that effect of R, right? So essentially, if I can append something here, which can give me a negative resistance. So let's say since this is in admittance, let me call this G. And if I can only get a circuit which gives me negative of G, then summation of, if I club them together, right? I'm good, right? No, I think something makes some mistake, right? Yeah, this is fine, this is fine, right? So admittance will go to zero. So you're good. So now the question is, how do I generate this negative of G? So clearly I mean, neither R, LC or any combination of that can generate, because negative of G, if you think about it, if you put in, what does negative impedance mean or negative admittance mean? If you put in some voltage, right? So it is going to generate a current in the opposite direction, which means it is going to give you back power, right? It's power generator, which means that none of these passive things will be able to design that. You will not be able to design any power generator using passive. So you will require some sort of actives. Fine. So we know active ways of designing many things. We have done other courses. So we'll resort to that. So now let's think about what is the simplest active device that we know, that is a transistor, right? When I say active device, nothing is actually active. Everybody takes power. But if I disregard the effect of biasing, then I can say that in the small signal regime, your transistor can behave like an active device. Okay, fine. So let's design an active device. So the goal is to design something so that when I put in a voltage here, V1 or V in, I should be able to get a current back in this direction, right? Which is equal to G times V in, right? Because if the current goes in the opposite direction to that arrow, if it's G times V in, then I'm getting a positive impedance or positive admittance of G. If it flows in the opposite direction, then I'm getting a negative impedance, right? So that should be pretty intuitive to understand that what needs to happen in order to get a negative impedance. Okay, so let's say I ask you using transistor, you have to generate the opposite, right? So the one that you are familiar with. So let's say I ask you to generate something so that if this is V in, current is in this direction proportional to V in. Obviously, you can put a resistor you can put a resistor which gets a current which is proportional to this. But let's say I do not want to put a resistor because ultimately with resistor I cannot go to the circuit on the left. So some sort of active device. What is the thought process? How will you go about doing that? Yeah, so diode connected. So why does diode connected solve the problem? Why does diode connected transistor help? In the sense, what I'm asking is, but when you say diode connected, you are essentially saying that I have a voltage controlled current source, because a transistor is a voltage controlled current source. So I assume I have a voltage controlled current source ready. A transistor is a voltage controlled current source because if I apply V in, I'm going to get a current which is proportional to V in which direction? Going out or going in? Going in, right? So I'm going to get something which we call GM times V in this direction, right? A pristine transistor does this, single transistor, right? So that's why we put a negative sign here. Like in case of a common source amplifier also, we say that it's when we want to replace a common source amplifier with a small block, we basically say that we'll use this notation. So when we say that I want to get impedance of G, or rather when I want to, if I put a incremental voltage source here, V in, the goal is to get a current in this direction, which is equal to G times V in. This is the goal, right? So obviously this goal is not satisfied in this configuration because input impedance is infinite, right? But if I have to, if I look at what is happening at the output side, right? So I am getting a current which is proportional to V in, and the proportionality constant is Gm. But this current in order to achieve my goal, this current has to come from the source V in. Correct? So what is the simplest way to do that? Yeah, so you just put it in negative feedback, right? So the current that goes in is G, in this case, Gm times V in. So there, in your case, your G becomes equal to Gm, right? All you have to do is to size your transistor or bias your transistor in such a way that Gm is equal to the G you desire, and you are done. Now we want to do the same thing to get negative impedance. Okay. So let's say we want to do the same thing for negative impedance. So what do I need to do? No, don't get into the configuration business as of now. So we are very block level, top level stuff. Right. So we have this. Now I want current in this direction. Okay. And again, we have a voltage controlled voltage source, a voltage controlled current source. So now walk me through it. I haven't put a sign anywhere. So you can also change the sign, let's assume, if the need be. So walk me through it. What do you like to do? You would like a positive sign. Why? Yeah. So this current will be Gm times V in this direction. And if I put it in this format, so this current G will be equal to Gm, right? So if in this case, G will be equal to Gm, and this R in will be equal to -1 over Gm, right? So you get negative negative impedance. Fine. But a transistor does not have this configuration of positive, right? So what do we need to do? So I essentially have this. I essentially have a voltage controlled current source. I mean, this is basically a dummy for a transistor, right? I have a voltage controlled current source with a negative sign, which means inherently inside, maybe you can think of a common source amplifier embedded inside, right? So what do I need to do to get from negative sign to positive sign if I have one negative sign VCCS available to us? Add another, right? One more flipping will do, right? So let's flip. So we have, let's say I have a GM here, but I need to flip using another voltage control current source. So I'll put something here. Let's say this is also of GM, but here I don't have any impedance now, right? So some issue, I mean, infinite and all those things can happen. So I'll just put some impedance for the time being, some resistance here. Okay. So if I apply V in here, the voltage that will accrue here will be how much? Minus GM RV in. So the current that will come will be in which direction now? Going out or going in? Out of value? GM square R in, and connected in this format, right? So what is the current that you are pushing in now? GM square V in, and GM square V in times R in, right? GM square R in times V in. So your effective G now is equal to negative 1 over GM square R in, right? So you get a negative impedance using, I mean, you can, if you assume these notations to be common source amplifier, you can put two common source amplifiers in a certain format, and you should be able to get negative impedance. Now, if I replace these with common source yes. Come again. G should be equal to minus GM square. Right. Yeah. So this is R, right? Correct. Yes. Thank you. Yeah. So now, if I replace these cute little boxes with transistors, I mean, you'll be able to figure out a configuration which I'm sure you have seen in some format or the other. So let's do that. So let's say the first common source amplifier. The first guy is a common source amplifier. So I put it in this format. I'm not showing biasing and all, right? So assume biasing is present. So this is V in. This is this node. Then I follow it up with another common source amplifier. So this also probably will have the same, I mean, if I have, the first one has a load, let's say second one also has a load. And then what happens? The output goes to the V in, right? Essentially, you kind of get something like this, right? So, and if I now make it slightly neater and flip it, right? Flip the first transistor. So it looks like this. So you have a load here, and you can take V in to be anywhere, right? This can be the V in. Okay. So this gives you a negative resistance from either of these terminals. You look at, I mean, if these two transistors are identical, right, and the resistance and the load are identical, there is no difference between the circuit on the, I mean, if you look at the left side or the right side of the circuit, they are going to give you identical they are going to give you identical impedances, right? Like identical negative impedance. Okay, so what will be the negative impedance in this case? It will be slightly different from whatever we saw. Why? Because now, if you think about it this way, the only difference here was the difference between this configuration and this configuration is that here we have an output resistance here we kind of neglected anything, right? So that gives the positive part of the impedance, an additional positive part of the impedance. So when you do the calculation, effectively some current will go into that and effective G will reduce by the amount of current that flows into that positive resistance. So that's an adjustment that you have to make. But I mean, so that's the only difference between the circuit on the top and the circuit on the bottom. Okay. Okay. So now, why did we come up with this? We wanted to cancel the negative impedance of, cancel the positive impedance of the RLC, right? So we have an RLC, so we have to put that RLC somewhere. So effectively we had this. Pardon? Tunnel diode, yeah, good point. So Aryu's point is that there are other devices, right, which sometimes give you negative impedances, negative resistances. Like if you check the IV characteristics of some of the devices, you are going to see they have negative slope at some portion of their IV cat, which essentially means that if I take a differential of that, small signal wise, they give negative impedance, and tunnel diode is one example of that. We can use tunnel diode, but the issue is it's not easily integrable in a CMOS substrate. Right? So because it is not easily integrable, we don't, tend to use that. If tomorrow some new device comes which is easily integrable in a CMOS substrate, we are going to forget CMOS and use that. Right? So it's all about how economic is it to design your, to integrate a new device. It's all about how much money it takes to fabricate a new device on a CMOS substrate, because CMOS is among all the technology that is available till now, CMOS is the least expensive, most economical way of designing analog circuit or any circuit, any integrated circuit. So if you are planning to say that I want a tunnel diode, which means I probably will not be able to use the same type of lithographic techniques, same type of mask to build the new device. I want some additional mask on it, and every mask is hugely expensive, right? So it can even double your cost or triple your cost if your mask is not easily integrable. So if that is one of the reasons tunnel diodes are not used. Another reason is, now I'm not sure about this reason, but I can guess the equivalent size of a tunnel diode for which you are going to get such a performance is much larger than the equivalent size of a CMOS device. So that is another problem, right? So, but at this point, I'm not particularly sure what is the exact dimension, but they are big. Okay. Okay, fine. So let's go back to this discussion. So we had some, I should say this RB now, because that was R initially. We have this R. All we have to do is to connect this node to this node. I have a common ground. And if I play my cards right and ensure that the looking in impedance here is exactly, it exactly cancels R. That is, the looking in impedance, looking in admittance is exactly equal to 1 over R. Then we are good, right? So, so ultimately, if you have to use such a circuit, you'll have to also take care of biasing, right? So, how do I take care of biasing in this way? Now, if you think about it, this is a small signal ground, right? This is a small signal ground. And the whole purpose of reason we put the RB is because we wanted to ensure that the transistors are in saturation and all those things, good things, right? Because ultimately common source amplifier configuration requires the transistor in saturation, certain amount of VDS and so on. So, but since we already have an inductor in the picture, I probably don't need that RB to give that biasing if I put the other end of the inductor to a VDD. Right? What I mean is, I can essentially do this. I can get rid of RB and put this entire thing here. Right? So I can do this. And make this VDD. So the small signal picture still remains the same. And your, if I call this M1 still gives biasing through the inductor. Correct? Okay. So we can as well do the same thing for the right hand side. I mean, there's no point doing it for one and not for the other. So I can as well do it with the same thing here. Another reason we want to do, I mean, one might say that this is probably not a very good idea because you are doubling the size of the inductor, which is correct. We are doubling the size of the inductor. But one of the reasons you would like to do this is because differentially, if this goes high, this goes low, you kind of get differential output for free. And as you must have seen in other circuit courses that you have seen, that you have done, differential circuits have a lot of advantages, right? In the sense that it can give you some sort of noise immunity with respect to coupling. It gives you kind of get rid of second harmonic distortions, right? So I mean, in 610 probably you are still not in 613 you're probably not in that stage as yet, but at least you should be able to understand that if in a differential circuit, right? So if let's say I have two signals, I have two signal lines going parallel to each other, and there is some sort of, let's say I call this V1, let's say I call this V2, and some sort of clock is going in this direction. Some sort of clock is going in this direction. Now, clock can be an interference or anything. So, and let's say the clock is underneath, right? I mean, they are not cutting each other, but one is, it's like a bridge. One is flowing below the other. So there will be some sort of capacitance between these two lines, right? So if the clock jumps, so the corresponding jump, some part of the corresponding jump will appear on V1 and V2, right? So if you only observe V1 and V2, you are going to see those jumps. But if I observe V1 minus V2, this will be clean. There will not be any jump, right? So this is one advantage of differential signaling. So for differential signaling, what you need to ensure is that V1 and V2 are opposite phases, because you do not want to also cancel out V1 and V2 by taking a difference, right? So V1 and V2 have to be in opposite phases. So every line that goes in inside your chip, if you can have a corresponding opposite phase running parallel to it, and you take the difference, then it becomes immune to any common excursions that happens in both the lines. So using the same philosophy, I would like to generate clocks which also have different phases, right, at a very broad level. So this circuit topology also gives you kind of the same thing, right? Whatever happens on one side, the 180 degree out of phase stuff happens on the other side. Yes. Okay, so the motivation is ultimately, I mean, why did we have RB? Just to keep biasing, right? We wanted to ensure that the transistors have sufficient VDS. If I already have an inductor, then it's getting a VDD, right? So why do I need an RB? I don't need. So even if I have an RB in this case, that will get shorted out for DC because the inductor will dominate, right? Okay, fine. So this is this type of circuits are often called voltage control oscillators, right? So these are called okay. I shouldn't say voltage control because I have not talked about what is voltage control. These are like oscillators for the time being. why is this an oscillator? Because it's generating an output, it's generating a signal without no apparent input. Right? It's oscillating on its own. It's like a simple harmonic motion or a pendulum which keeps on oscillating forever without giving any apparent input, right? General question, if it's generating an energy from where it is coming from, like it's actually not generating any energy, right? Nothing can generate energy from nothing. Somehow some initial condition should be there, but that initial condition can die off, right? Yeah, but right now it is not dying off. So where from is the energy coming from? Right.
So to have, if they are going to be ideal, then we can have a charged capacitor. If first charge the capacitor, then make a tank circuit. So
right.
If it is ideal, it's going to sustain oscillation.
Right.
At the same amplitude. But since because of the non-idealities of those inductors and capacitors, so because the amplitude dies out because of the positive resistance,
yeah.
Now we are the initialized capacitor, which is already charged. Now that is connected to this tank, this cross-coupled battery.
Sure.
So these nodes across whatever the black dots nodes will reinforce the initial conditions, because any attempt to change the nodal voltage
sure.
will be in the negative feedback that will be taken care.
Sure.
Because if we try to
understand everything that you said, doesn't answer my question.
That is the negative.
Agreed. Where from is the energy coming from? Yeah, somebody said VDD. Right? Yeah, obviously, I mean, if you don't find anything, everything comes from VDD, right? So that's the source. You take away VDD, nothing is going to oscillate. Okay. So ultimately the energy is coming through the negative resistance, and where from the negative resistance is getting the energy? It's coming from VDD ultimately. Right? Okay, fine. So this is an oscillator. Now the question is, how do I? So again, this is the oscillator is oscillating at a frequency of 1 over under root 2 pi under root LC. So if I have to change the frequency of oscillation, right? Because why do I need to change? Because ultimately in the receiver you have a mixer which is trying to align its center frequency to whatever it's coming to, whatever is coming at the input. Now whatever is coming at the input can be from different bands. Right, so you don't want to have one LC oscillator each for very small change of bands, right? Let's say your band changes by 10 megahertz, right? You don't want to have another LC oscillator which is at 1.001 or 1.01 gigahertz, and one at 1 gigahertz, one at 1.2 gigahertz, so on, right? So ideally, you would like to reuse the thing that you have. So how do I ensure that one LC oscillator, this configuration, can help us in giving oscillations at different frequency? Obvious answer is change L or C, right? So that's the one that is setting the frequency. If I am able to change L or C or either both of them, then I should be able to get oscillator operating at different frequency. Now, as it turns out, it's not very easy to change L, right? One of the impediments of CMOS, among all the good properties that CMOS IC design has, L is not one of them, right? L is something that unless you have to, for whatever reason you have to use, you don't use. But in this case, there is no other way, you have to use, right? So you have to use L, but once you have an L, don't tweak it, right? Have it, whatever it gives, you live with it. Whatever loss it gives, you live with it, but don't add more to it. The moment you try to tweak it, you are going to add something and it will mess up your circuit. So if L is out of bounds, right? Once you have fixed an L, you have an L. The only thing that you can change is the capacitor, right? So one way to go about changing is having banks of capacitors, maybe have multiple parallel capacitors and tune in and out each of those capacitors as you please. That is one way of doing about it. Another way of doing, but that is a discrete way of going about it, right? So you let's say you have banks of 1 picofarad capacitor, 10 of them. In one configuration, you turn on all 10. You get a 10 picofarad cap, corresponding you get an FC. In another configuration, you turn off 9 of them and have only 1 of them. Then you get 1 picofarad cap. You get a different FC, right? Maybe under root 10 times higher FC, right? So you can get different values of FC, but they are not continuous. There will be some difference between the jumps because you can go for 10 to 9 to the capacitance values are changing discretely. So correspondingly, the FC values also change discretely, and that might or might not be acceptable. Okay, so but there is a continuous way of changing the frequency, which means that you need a device which can change the capacitance also in a continuous manner. Do you know of any such device? Miller capacitance is it's a capacitor, right? I mean, it's one of the configurations. That's not a. I mean, okay. Okay, and you change A. Okay. So his suggestion is that you take an amplifier, connect a Miller capacitance, and you change in it. So note that these have to operate at multi-gigahertz frequencies, right? So can you get a decent gain, which is so? Okay, let me address that. So you are assuming that you have a C. So the impedance that you are seeing is 1 by 1 plus A times SC, right? What if A is a function of frequency? Which it will be, because ultimately you are making it through through devices, right? So basically 1 plus A of S times SC. Now looking in impedance, is it a capacitor? No, it is some weird thing. Part of it is probably capacitor. So that's why Miller capacitance ironically works only for low frequencies. I mean, you can basically say that I can use this configuration to mimic a capacitor only at very low frequencies where A doesn't change. A is constant. If A is also a function of frequency, then it's not a Miller cap anymore. Okay. So, but that's a good point. So now this is out of bounds. Any device, MOSFET, right? A varactor. Right, a varactor, you can use it as a continuous variable capacitance. Why? Because ultimately, and without going into device physics, so if I have some biasing between these two nodes, let me call it some VCM. Now, depending upon if the device is in depletion or if the device is in inversion or accumulation, you can get different types of capacitances, right? So a very high frequencies, the capacitance kind of looks like this. At low frequencies, at inversion, it comes up. This is a low frequency stuff, but we are talking about high frequency, so we don't have to bother with the low frequency, whatever is happening. So here we have accumulation phase. Here, this is, I should say C, right? So C effective. And this is VCM. When VCM is 0, that is in accumulation mode, you have Cox times WL, I should say by WL. And here you get C depletion, right? So, which essentially means that if you operate somewhere here in this region, you kind of are getting a continuous curve, which gives you a continuity of capacitances without any gap between whatever capacitance you want. For that, what you need to do, you need to vary the biasing across the capacitors, right? So, which essentially means that I need to replace this capacitor with that varactor, with that MOSFET, and I have to ensure that it is biased properly, right? So, if we do that, what do we get? So, this guy remains the same. Put the MOSFET here. And maybe you control this node with some VB. I have used VB somewhere, so I'll just use VCAP, let's say. Okay. So I change VCAP, I'll be able to change the frequency of oscillation. So that's why now it is a voltage control oscillator, right? So I should say this is a voltage control frequency control. Voltage controlled frequency. Now, typically, we don't call it voltage control frequency generator. We call it voltage control oscillator. Okay, or it's a VCO. In short, we call it a VCO. And this entire thing is replaced with a symbol which looks like this, where here we call this V control. And at the output, you have oscillations at some frequency, right? So we call it some, maybe FC in this case. So this V cap is the V control. And the output you get some waveform of frequency FC. Now, the thing that you should keep in mind when I draw an oscillator in this way, when I write something as FC, even though it's obvious, but you should keep this in mind, the output is a sinusoid of frequency FC. If I change V control, the frequency of the oscillation changes and not the amplitude. Okay, I haven't talked about who sets the amplitude in the oscillator, right? That we'll come to that when we talk about oscillators in some amount of detail later on in the course. But let's assume that for now, the amplitude is set by something, some sort of initial condition or some limits on the power supply, some sort of limit is setting the amplitude. But the key thing that that you should note from the discussion thus far is that you have this block whose input is a voltage control, output is a sinusoid of certain frequency or not changing frequency, certain amplitude or not changing amplitude, but it changes with frequency. So again, picture is worth 1,000 words. So essentially what I'm saying is, if I have this VCO and with respect to time, I change V control from some voltage to some voltage, very slow rate, right? So at a very slow rate, I keep changing this. What I should see is, maybe slope is too much. At the output, what should I see? This is V out. At V out, what should it look like? With respect to time, what is K times VCO? With respect to time, what should the output look like? Sinusoid with varied frequency. Now, I have not told whether increasing V control increases frequency or increases V control reduces frequency. It can be either way, just like in any feedback loop, you go about doing it. But let's assume in this case, it increases frequency, right? So I can assume that because in this particular case, if V control is V cap, if I increase V cap, I am kind of pushing the transistor maybe towards depletion region, right? So it should be the other way around. A depletion region, which is reducing the cap, right? So then it can increase, right? So, but depends upon which regime you are in. So whether, again, if we use PMOS, it will be something else. If we use NMOS, something else, so on. So, but the key point is that let's assume that it increases, right? So it might as well decrease, but let's assume it increases. If that is the case, so your output should look like something like maybe something which is very difficult to draw a continuously increasing frequency, but you can assume something like keeps going, right? Fine. So that's kind of a good way of generating a controlled oscillator, voltage control oscillator. If I want to settle to some frequency, I stop increasing V control, and then it is going to settle to one particular frequency. Okay, fine. So it looks like we are done with VCOs, but there is a problem. The problem is, you must have seen this with your analog clocks that you have in your homes, or if you still use. You have the center, it goes back and forth with respect to whatever the GPS clock is, right? You set it to something, you are maybe after 1 year, it goes 5 minutes in advance or 5 minutes delayed, and you are late for class and all those things, right? So why does it happen? Because it also has a VCO, some sort of VCO, but its center frequency keeps on drifting. So how does a clock work? The clocks that you have in your watches is basically, it sees how many clock cycles, it counts the clock cycles essentially, right? So one clock cycle is 1 tick. You can assume, to be very simplistic, let's say one clock cycle is 1 second. So how many ticks you count, that is the time. Okay. So if the rate of count changes, the interpretation of time changes, right? So same thing happens here. Because of reasons, beyond your control, right? So folks who are masters and devices will know. So your values of LCs and everything keeps on changing with they are not constant, right? So you have something now, you fabricated something. Maybe after 5 minutes, it will probably change to some value which is maybe 1 ppm away from your whatever you design. After another 5 minutes, it will probably change to something else, and keeps on happening, which essentially means that you will not be able to tune your center frequency to exactly what you want. And that is important because if your center frequency shifts, then what happens to the receiver? If your center frequency shifts, if this FC changes by even, let's say, 0.1%, and we are talking about 1 gigahertz FC, 0.1% is 1 megahertz. 1 megahertz. And your FBB was to start off 1 megahertz. So essentially, you can filter out your signal completely, right? So this is not something that you can take the risk of, right? So that's why, just like anything in IC design, if you have these type of issues that you want very precise something, in this case, you want very precise oscillation, very precise oscillator frequency, you have to have some master somewhere which does not change or changes at a much smaller rate than whatever is inside the chip, right? So just like in case of when you wanted to design, if you want to, let's say, get a voltage gain, or let's say your requirement for some reason is a very stable output of, let's say, 2 volt. Now I'm going to, again, good old voltage amplifier domain, right? Not VCO. Let's say I want 2 volt, extremely stable output. Is there anything that you can do with staying inside the chip that gives you constant 2 volt amplitude, constant 2 volt DC output? You will use negative feedback, right? So you are going to use negative feedback. So what do you do when you use negative feedback? You take this 2 volt and then compare it with something. What are you going to compare it with? 2 volt. And who generates this 2 volt? Some reference which comes from outside. So you have shipped up your problem to somebody else, right? Give me an accurate reference, I'll give you on-chip accurate 2 volt, right? And there's nothing wrong with that. We do that, right? So there are, among all the bad things that discrete components have, one very good thing is they're very reliable. You can design very reliable specs using discrete components, just that they are very big and bulky and doesn't really operate to very high frequencies. Those are some of the bad things. But you can get very reliable sources from outside. Okay. So essentially, in this case also, you would need a very reliable oscillator somewhere else, right? And that is we typically use them, and they are called crystal oscillators. Their center frequencies are extremely reliable. And when I say extremely reliable, they probably will, if you tune it to probably 10 megahertz, they are going to probably shift by 1 ppm across maybe a few minutes or so, right? So I might be misquoting some numbers here. Chitra, can you back it up? Okay, right. So I underestimated its accuracy. So it's basically extremely reliable. So which means that if I have something off chip which is extremely reliable, I'm going to use it to generate my on-chip references. Now, the question is, you might ask that if I have something reliable, why don't I use it directly? Why do I need to bother with something here? The same answer to the same answer is the same thing. When you have this 2 volt off chip, why do you need why do you need a buffer on chip? Couple of reasons. One is loading, right? And second is you need not necessarily want 2 volt at the output. If you want, let's say I want a 4 volt at the output. I want 4 volt at the output. What are you going to do? You are going to, so if let's say I sketch it in this way. So my available input is 2 volt and I want 4 volt. So what do? I divide it. Yeah, some sort of divider. in this case, divide by 2, and then compare it. And then put some sort of amplifier. Typically, I mean, the characteristic of the amplifier is an integrator. You put an integrator, and when the system settles, an integrator has an infinite DC gain and so on, your output will be 4 volt, right? So just like this, in case of a crystal oscillator, it is very difficult to get very good crystals operating at gigahertz frequencies. Crystals are again acoustic devices or piezoelectric type of devices, not acoustic, piezoelectric type of devices. So they do not operate at multi-gig frequencies. They typically operate at megahertz. More expensive ones operate at probably 100 megahertz or so, but typically the stuff that you have in your cell phone will probably operate at megahertz, tens of megahertz or so. But you still need something of the order of gigahertz, few gigahertz, right? So if I use the same philosophy, right? If I use the same philosophy to design a stable on-chip reference, which means that I would need an input, which is a crystal. So this is a crystal, which is a stable reference, which gives me some sort of very accurate sinusoid or whatever, right? It gives me some frequency. Let me call it a sinusoid. So Vp sine omega t or omega ref t or 2 pi f ref t, where f ref is extremely stable, no change, right? Let's assume no change. I want output to be Vp sine 2 pi times n f ref t. I want to multiply the frequency by factor of n, right? So using the same philosophy of negative feedback voltage amplifier, what do you need to do? You need to convert this guy output, you have to divide it by factor of n. So I need some sort of division. Note that this is not a voltage division, this is a frequency division, right? So this is a frequency division. Now, if you have instead of Vp sine omega t, if you have a square wave, right? If you have a square wave whose fundamental frequency is still f ref, or rather n f ref in this case, let's assume. Let's say n equal to 2 for the time being, right? And I want to generate a frequency which is half of this waveform. What do you need to do? You need to basically, what would it look like? It would look like, it's like skipping 2 cycles and generating a waveform which is double in time, right? In time period, which can easily be done using digital counters, right? You design a state machine, you don't look at, you skip 1 cycle and so basically this divide by n is a digital counter. Okay. So you have here, what do you have here? You have, if this is f out, we still don't have NF ref, this is f out. So you have f out over n, and you need to compare these 2 frequencies in frequency comparison, not voltage comparison. Mind you, voltage is still maybe VDD or maybe whatever, VP. So at the output, I want something whose frequency component is f ref minus f out over n. Among all the things that you would have known, we have been discussing till now, can you suggest something that can generate this? Clearly, subtraction in voltage domain will not do because that's a linear operation. It's an LTI operation, right? So inputs are waveforms of 2 different frequencies. I want an output in the subtraction of those 2 frequencies. So what can I do? I can mix, and then only mixing will not do. I need a filter, right? So I can mix and filter, right? So I'll do that. So I can do mixing. And some sort of filtering, so that it only takes out f ref minus f out over n and nothing else, right? So this should have only, this is f ref. So the tradition is to keep only the variables in the, when you are writing the loop, you only keep the variables of interest in the loop. Voltage is not of interest, time is of not of interest while finding out this loop. So we'll not keep track of that. So this is f out over n. We'll see. So So here I have fref plus minus f out over n, and then maybe other harmonics of these and so on, right? Because you can have. So we put an LPF at fref minus f out over n, right? So where f out is the desired frequency of interest, obviously, right? Otherwise, there's no point. Which means in this case, your desired frequency of interest is what? NFref, right? Which means your LPF should have bandwidth of what? Ideally, if the loop has to work, we have not yet completed the loop. If the loop has to work, what should be the bandwidth of LPF? If f out is supposed to be NFref, no, if f out is NFref, then fref minus f out over n is what? 0, right? So essentially, it should only be passing DC and nothing else, right? It has to be extremely small bandwidth, right? Only DC, no other component. Okay. So this goes here. And now again, if I compare this with the normal voltage, normal loop, the voltage loop, this loop. So what did you have here? Okay, so we essentially, if I do the comparison, we are here now, right? So this is equivalent to there. So what do we need after that? We need an integrator, right? So now, as it turns out, I mean, you can put an integrator there. So let's put an integrator. Now this integrator, now we are in voltage domain kind of, right? So because we have a DC output, there is no frequency there anymore. Frequency of 0, we have a DC output. So you put an integrator. Okay. So you put an integrator, then the output of the integrator has to, in this case, is driving the final output. But in this case, we cannot, right? Ultimately, the integrator output is a voltage which will keep on ramping if the input to the integrator is DC. But as Dhruv pointed out, we need something at the output to generate that final waveform of the, fref times n, right? So this is a voltage. I have accumulated the information of error, but now in a voltage domain, I want output to be a frequency. What should I put? A VCO, right? So I put a VCO. And this voltage, this control voltage, this is the control voltage. This is the VCTRL. It goes and controls the VCTRL of the VCO, and you close the loop. Okay, so this is, when the loop settles, this will be NFref. I mean, I'm not showing the operation. I mean, if you do the analysis, assume ideal integrator and all, the only possible solution, just like in a voltage loop, is n times Vin. In this case also, it will be n times fref, but in a frequency format. Yes.
The integrator doesn't impact the fref minus f out by n, right? It impacts only voltage.
So this is a voltage domain. So the thing that you have to keep track is where I am talking about voltage domain, where I am talking about current frequency domain. So here I am interested in voltage. So here also this is voltage, right? So here I'm interested in frequency. Here I'm interested in frequency. Here I'm interested in frequency.
Same as the input, right? At the output of the integrator,
no, integrator input is DC, right? Because low pass filter has almost 0 bandwidth. And output of the integrator is also DC, right? You are integrating, you are ramping, right? The only way the ramp can stop when the loop settles to the value that the VCO wants to get NFref. Yes, right? So because ultimately what is V control? V control is this guy. Okay, so you connect the VCO inside the loop. So by the way, this loop is often called phase lock loop. Again, I will not define why it is called phase lock loop, but this is often called PLL, but a phase lock loop. It's just a negative feedback loop in a frequency domain. The intuition behind why it is called a phase is essentially this, right? So if you combine this guy, okay, if I combine this guy, between the input and the output of this guy, what am I seeing? I am essentially finding the frequency, right? I am essentially finding the difference in frequency, low pass filtering it and integrating it, right? So in a way, I am integrating the frequency, right? In between, I have a low pass filter, but I'm integrating frequency with respect to time. If I integrate frequency with respect to time, what do I get? Phase, right? So that's why this entire stuff often is much simplified. You don't put actual mixers and all. There are some versions of that. You essentially put something which can detect a difference of phase, and you try to align phase using negative feedback. That's why it is called a phase lock loop, and we're going to see that later on. Okay. Any other questions? Okay. If there are no, then we'll have a quiz.